myself Abdul Rahim Jamali. I'm a student of Bachelor's in Electronics Engineering in Zakir Hussain College of Engineering and Technology, Aligarh Muslim University. So today I'm going to present uh, our digital IC design assignment, which is true single phase clocked positive latch, which is TSPC Positive Latch in Cadence Virtuoso. It is done under the C2S Chip to Startup project at ZHCET AMU, funded by Ministry of Electronics and IT, Government of India. First of all, I would like to uh, present immense gratitude to our mentor, our teacher, and our guide, Dr. Muhammad Wajid sir, for his immense support throughout the process. Without him, it was close to impossible for me from solving each and every bug which I have faced throughout the process. His constant support made this possible. So let's start. So first of all, we have to go into the remote desktop connection. So let's click into remote desktop connection. So I will open it and I will connect it. Now press yes, enter username and password. Click on OK. Again, one more password to unlock our CentOS 7. So finally our CentOS 7 has been opened, and first of all you just have to do right click and click on new folder. And while making a new folder, make sure that your folder does not have any space. If you have space, then rather without using space, you better use underscore. uh, since I already have made a folder, so I will just press cancel. My folder, which is here Cadence, I will double click, and here you just need to right click and click open in terminal. Now here you have to write csh, enter uh, source space slash home slash cadence slash cshrc. This is what you need to enter, type and enter. After that, type virtuoso space ampersand and click on enter. As we will do these processes, our cadence log file opens. Here is our log file which has been opened. First of all, click on file, click on new, click on library. We will create a new library. So let's make a library. Let it be abdx045. This is our library. So while naming the library, we have to attach it to an existing technology library. uh, or whatever the technology we are using, whether it is 180 nanometer technology or 90 nanometer or 45 nanometer. Accordingly, we have to attach to existing library. Since I have designed on 45 nanometer technology, so I will prefer GPD045 technology file. So click on attach. Since I have already made the library abdx045 and I have attached the library file, so it shows that library already exists. So I will close it and I will just cut it. After creating the library, you just need to click on file, click on new and click on create cell view. And here you just need to make sure that your library is abdx045, which I have recently generated. Now in cell, you need to create a cell using any name. You can use test also. You can name it by your circuit schematic name also. Since I have already made, so I will just cut it. After making these two things, you just need to click on again file and open. I will select my library which I have created, abdx045, and here I need to click on TSPC underscore pos underscore latch. This is the cell which I have created, and I will click view as schematic view in order to see the schematic which I have already designed. Click on OK. Now click on session, and now maximizing it. Here we have our TSPC positive latch. First of all, I will press F so that it perfectly aligns with the screen. And brief introduction about the TSPC positive latch. Basically, TSPC stands for True Single Phase Clocked Positive Latch. TSPC is a kind of dynamic CMOS logic style that uses only one clock cycle uh, to control both pre-charge and evaluation phases. It stores data when clock is high, and it holds the data when the clock is low. TSPC consists of three stages. The first stage is dynamic NMOS stage, input sampling for input sampling, and we have a PMOS keeper stage, which is here, and we have the static CMOS stage, which is here. So in short, we have this kind of arrangement in TSPC, true single phase clocked positive latch. We have two PMOS and we have two NMOS, and in positive latch again we have this NMOS. This PMOS source is attached to VDD and its gate is attached to input voltage Vin. Source of this PMOS, sorry, gate of this PMOS is attached to uh, drain of this PMOS is attached to drain of this NMOS, and uh, these two drains are connected to the gate of the second stage PMOS, and source of this NMOS and drain of this NMOS are connected again, and it is then fed to the uh, NMOS at the second stage, and sources of these two NMOS are connected to the ground rail. This is in short about our TSPC positive latch. So I just need to check whether our circuit is perfectly fine or not. So for that we will do check and save process, and now we will see the log file. Click on the C icon, and here we can see that schematic check completed with no errors, and TSPC pos latch schematic is saved. So now we will move further. Our schematic is correct. Now we will move towards the test bench generation. So for that we need to click on file, then new, then again we will have to enter into abdx045, and we just have to make the cell which is tspc underscore pos underscore latch latch underscore tb, which is already I have generated. So rather I will press cut since I have already made. So I'll click file, open, and here I as you can see here that I have already created tspc positive latch underscore tb test bench. So I will view as a schematic and I will press on OK. This is our test bench. Here we have the voltages, input voltage V in, clock signal CLK, and the supply rail as VDC, ground rail as GND, which is VSS here, and here we have the output node, and here we have the voltage sources like VDC, DC voltage, and we have two pulsed voltage sources. So for selecting the voltage, we just need to click on create instance, and we just need to select the library which is analog lib, and in cell you need to do VDC. uh, After clicking VDC, press on hide, and our voltage source is ready to be placed. Since I have already placed, so I will press ESC escape, and after pressing the voltage source VDC, click on VDC. It gets highlighted, then click on Q properties. After that, here you have to put DC voltage according to the maximum supply voltage of your file. So I am using 45 nanometer technology, so I will use the DC voltage as 1.2 volt, and then click on OK. After that, we need to select these two voltages where we can apply the input pulses. So for that, I will click on this, and I will press I will select V pulse. So as I am writing V pulse, click on V pulse and click on hide. So our this is ready. Since I have already uh, mm, uh, placed these two voltages here as well as here, so I will just click on escape to get rid of it. And after that, for configuration of these two pulses, click on this. When it gets highlighted, right click, and then click on Q properties, and name the voltages like voltage 1 to be 1.2 volt, voltage 2 to be 0 volt, and period to be 40 nanoseconds, and pulse width to be half of the period, which is 20 nanoseconds. After configuring this much, click on OK. After that, after configuration of the clock, we will configure the input voltage. So click on the input voltage. After it gets highlighted, right click on properties, and now configure it in a way like voltage 1 is to be 1.2 volt, voltage 2 to be 0 volt, and period to be 20 nanoseconds, half of the period which we have applied to the clock signal. And pulse width, of course, half of the period, which is 10 nanoseconds. After that, click on OK. By doing these things, our test bench is ready. Now we will see the correctness of the test bench. So for that, we will click on check and save. So click on check and save, and we will refer to the log file, which is C icon here. After clicking it, we can see that here we can see schematic check completed with no errors, and I can see ABDX045 TSPC POS latch test bench schematic is saved. So I have no errors, and our schematic for the test bench is already saved. So we will move further towards the simulation part. So let's simulate. For simulation, we have to click launch and ADEL. Uh, Click on ADEL. Now we will click on session. Again, we will click on session, and again we will click on session. So we have ADEL tab, which is here. I will click. After clicking this, our this tab opens. In this tab, in the analysis part, in this, I will move my cursor here, and I will right click, and I will press on edit, and I will uh, click on tran to run the transient simulation, and stop time, let it be 80 nanoseconds, which is uh, twice the maximum time period. And I will keep accuracy defaults to moderate, and I will click on OK. So our setup for transient is ready, and here for output, we will click on right click in this tab, and we will click on edit. After that, in the expression part, I will select from design, click on from design, and here I will select VDC, and then move the cursor towards clock, then click on clock CLK, and after that place the cursor towards the V out and click on V out, and now click on ADEL tab. I can see that here we have these three things selected: PDC, clock, V out. And apart from that, I also want to run the DC simulation. So for the DC simulation, now right click here, click on edit, click on DC. In the DC simulation, click on save DC operating point, and click on enable, and click on OK. So here we have the DC, but we cannot see. We will edit this DC, and we'll click on options. So here we have multiple options. So rather we will leave the DC simulation. We will just click on cancel, and we will just uh, click on design variable, yes. And here variable name, so I will select the design variable as uh, select design, no design variable here. So variable name, let the variable name to be my input variable, which is vin, in our design variable. So here in ADEL part, uh, design variable. So we will rather prefer, after selecting the transient, I will just rather I will click on right click, then edit. After that, here we need to click on DC. Now click on save DC operating point, and click on component parameters. Now click on select components, and now here we need to select on click on this voltage source VDC, and now we have to click DC VDC voltage, DC voltage, then click on OK. After that, click on choosing analysis, and we have our voltages V not being selected. Now click on start time, start voltage to be 0, and stop to be, let it be 1.2. And now you need to just click on OK. After that, let's select this. Our DC simulation has been here, and let's now simulate. For simulation, you just click on this play button. So I will just click on this. So our simulation is being run. After our simulation has been run, so we'll just maximize it, and we'll see both the behavior of it. So here you can see we will just split the traces. So click on right click, click on split current strip, click on trace. So here we have our voltages, but here I can see the output is not changing. So what might be the reason for that? So I don't know exactly, but I will have to. After doing this much process, to simulate the transient response, we have to just click on this play button to run the transient. So click on this. Our transient is getting run. So this kind of response we are getting. So first of all, we will just do split current strip, and then split the trace, and now we can see that it's not being splitting. But why? First of all, click on launch, So I will click on uh, the launch, then ADEL. After that, click on ADEL here, then right click here, then click on edit, uh, click on the tran for transient analysis, click on the stop time to be 100 nanoseconds, accuracy defaults to be moderate, click on OK. After that, in this tab, right click on edit, and then in expression click on from design, and then select VDC, select clock, click on clock, and select V out, click on V out, and then finally click ADEL. Now we will see that our outputs have been selected: VDC, clock, and Vout, and transient response is also we have selected. To run the transient response, we will just click the run button. So we'll click it. So our transient is running, and this kind of response we are getting. So right click, split current strip, and then we will click on trace. So this kind of output we are getting. So let's analyze the output. Here we are getting VDC not to be uh, fluctuating. So let's fix this VDC, why it is not being fluctuated. So let's analyze what might be the reason behind not working of the VDC. So वी हमें VDC नहीं लेना था यार वी now we will proceed to the transient analysis. So for that, click on launch, click on ADEL. Now click on ADEL, which is here. Now in this analysis tab, just right click on edit, and just click on tran to run transient analysis. Select the stop time to be, let it be 80 nanosecond, which is twice our maximum time period, which was 40 nanosecond as per our schematic. Click on accuracy defaults to be moderate, and click on OK. Here the transient setup we have done. Now in the outputs tab, right click on edit, and in the expression click on from design, and from design click on V in, click on clock CLK, and finally click on V out, and then click on ADEL. Now we can see that our transient setup, V in, clock, and V out all are here. So we just need to click on this play button for the netlist and run. So our transient response is running, and output is being shown here. Now right click on split current strip, and click on trace. So we have splitted the trace, and now we are getting a perfect transient response. Let's analyze the transient response. This is our clock signal, which we can see, which whose pulse width was 20 nanoseconds and time period was 40 nanoseconds. For the V in, our pulse width was 10 nanoseconds and our time period was 20 nanoseconds. Now we have, when we have V in 0 and clock is low, our output is high. When our V in was high, clock was low, our V out was again high. When our V in was low, clock was high, our output was low. Likewise, we can analyze all the possibilities from 0, 0, 0, 1, 1, 0, and 1, 1. Our output perfectly matches to the expected transient response. After that, I will cut it, and I'll move towards the DC response. The DC, for the DC in the analysis part, I will just right click, edit, click on DC, and click on component parameters, and in the component name select components. While selecting the components, we will click on VDC and Now we will click on again VDC and click on OK. While we clicked on OK, we just again go to settings output. So we have to move in ADEL transient, it's not. So yes, now we can see that our component V0 has been selected. Now we have to select the sweep range. So we will start from 0 and we'll move towards our supply rail, that is 1.2 voltages, and we will click sweep type automatic. So let it be automatic sweep and click on OK. And since we are interested to calculate the voltage transfer characteristics, so we will untick the clock, and after that we will just untick the transient also, as we have seen the transient behavior. So after that we will click on the play button to run the DC response. Our DC response is being run, and this is our final DC input output response, which we are seeing here. So after that, let's move towards the second part of the video, which is the layout part. So for the layout part, we will just uh, click on the launch, click on layout Excel, and we will just create a new layout and then draw the layout, and then run whether the layout has uh, errors or not. Since already we have made the layout, so we will just rather skip this process, and we will just click on open existing to open my layout. So click on OK, and here I have made the layout TSPC POS latch underscore LT. So I will just click view as layout and click on OK, and click on session again. And now this is our layout, as we can see. So after maximizing it, I will click on F to get it into full screen, and this is our layout. In the second part of the video, we have to demonstrate the layout. We have to check the DRC design rule check, the ERC, the LVS layout versus schematic. Then we need to see the parasitic extraction, and after that the GDS file. So first of all, we will just double click the folder Cadence, and here we will just right click, open in terminal, and CSH, enter, source enter, and virtuoso ampersand enter, and our Cadence log file has been opened. So at the very first we will just click on file, and we will click on uh, open. Here we will just click on our library abdx045, and here I just need to click on TSPC POS Latch LT, which was our layout earlier. So we will just click on OK. So click on session. So this is our layout of this schematic. We'll just compare both of them. So in our schematic, we have this PMOS. So here this PMOS has been placed here. This PMOS, the source of the PMOS, as we can see, is connected to the VDD rail. So the source of the PMOS is connected to the VDD via this metal layer, and the after that we can see that we have this PMOS, this NMOS, which has been placed at the middle of them, uh, which has of course a good reason for it to be placed here, which I'll explain later on. and the bottommost NMOS has been placed at here. The reason behind keeping this NMOS in the middle is very simple. As we can see here that the gate terminal of the PMOS as well as the gate terminal of the NMOS has been connected to common input, which is V in. So in order to make it simple, we have just placed this PMOS and this NMOS uh, as here and here, so that we have connected the gate via polysilicon uh, to both a common input, which is V in. And after that, we can see closely that the drain terminal of the PMOS is connected to the drain of this NMOS. So this drain of the PMOS has been connected via net to the drain of this NMOS. And we can see that this NMOS has been connected to clock. The gate is connected to clock. So the gate of this NMOS has been connected to clock via this polysilicon line. After that, we can see that the source of this clock has been connected to the drain of this NMOS. So we can see that source of this NMOS has been connected to the drain of the bottom NMOS. Finally, we can see the second stage, which our second stage is here. So in the second stage, we have one PMOS and we have one NMOS. So our PMOS is here, NMOS is here. We can see the source of the second stage PMOS has been connected to VDD. Source of this PMOS of the second stage has been connected to VDD via this metal layer, and the gate of this PMOS has been connected to the joint of drain to drain of these two transistors. So we can see that gate of this NMOS has been connected uh, the to the joints of these two drains here. And finally we can see that the gate of this NMOS has been connected to the source of this NMOS and drain of this NMOS connection, which we can see here. The gate of this NMOS has been connected via this to the joint of these connections. So this was our layout of this. Now finally we have here output V out. So we can see that our output is being taken from the drain of these two transistors. So the drain of these two transistors have been shorted via this metal layer, and we are getting the output from here. So now I will maximize it, and I will just click F to get into full screen. After that, I will just press E from the keyboard. So as I will press E, so we can see as I will press E, I can see here we have start 0 and we have stop to be, I will just select it to be 10. In display option, if I do this, so I will see that in our transistors the bodies are detached. These were the bodies. So this is the detached view, where we can see all the four terminals of each of the transistors, like gate, drain, source and body. So this was our layout. So we will see our whether our layout meets the design rule checks. So for the design rule check, or DRC, we will just click on Asura, which you can see here. So here we can see, first of all, we have to attach technology file, which I have attached, home slash cadence slash foundry slash analog slash 45 nanometer slash Asura tech lib. You can see configure while clicking on these options and accordingly going into it. So after selecting this path, we will just press OK. Now again click on Asura and click on run DRC. And here select the library to be the name of our library was ABDX045. Cell name to be TSPC Pos Latch LT, and view as layout. After that, click on the technology file to be GPDK045. Finally, click on OK. So then click on overwrite. OK. Click on again OK. DRC is running. Now click on, do you want to view the results of this run? So yes, click on yes. Now we are getting no DRC errors found. Now this confirms that our layout matches the design rule checks. So in design rule checks, basically the spacing between the metal lines, polysilicon lines, and various design rules are being checked. Now we have to confirm whether our this layout uh, exactly belongs to the layout of the schematic which we have generated for the TSPC positive latch. For this we have LVS, layout versus schematic check, which confirms uh, whether this layout is exact replica of the schematic. So for that we will just click on Asura. Then we have to click on run LVS. LVS stands for layout versus schematic. So click on run LVS. Now here we just need to enter our library file abdx045. Here we have the cell for our schematic. View as a schematic, we can browse also. So this was our earlier schematic which we are going to place here. So we will click on close. After that here click on the library to be our library name like abdx045 in my case, and uh, write down the cell of the layout. So the layout name was TSPC Pos Latch LT in my case, and view as layout. We will see whether this is exact layout. Yes, it is the layout which we wanted to confirm. I will just click on close. In the technology file, if it shows undefined, so we'll just click on GPDK045, and here rest all the things to be same, and we will click on apply. After that, click on OK and click on OK. So now just click OK to override. Uh, Click on yes, and finally we will just click. LVS layout versus schematic is running, and we will see whether our layout is exactly the replica of the schematic or not. So yes, now we got the output which confirms that we have total DRC violations to be 0, and here you can see our DRC violations are 0. Let's see whether it matches or not. So if we click on the LVS debug, so we will see schematic and layout match. This confirms that uh, our schematic exactly matches the layout which we have designed here. So by doing so, our LVS layout versus schematic process has been done. So after that, I will show you how to check the parasitic extraction. So for the parasitic extraction, we just need to click on Quantus, and again set up Quantus. So while doing setup Quantus, we have to set as default to be Spice, and technology to be GPDK 045. and rule set as default, template to be as it is. So uh, just cut this. After that, we will again press Quantus. We will run Asura Quantus. So while performing run Asura Quantus, uh, technology should be GPT K045. Rule set should be RCX typical. So we will just click RCX typical, and we have our parasitic extraction to be uh, resistor, P capacitor, P inductor, like this. And at the very end, we have extraction to be here. In extraction, there should be RC, and temperature should be 25 degree. Reference node should be GND exclamation mark, and capacitor coupling mode to be coupled, uh, and rest all things are same. Enable HRX should be enabled, and filtering, you don't need to change anything in filtering. In net listing, again you just ensure that all these four should be not do not include, and run details. You don't have to alter anything here, and substrate you don't have to do it. You will press OK. Your parasitic extraction will be done, and you will clearly see the uh, parasitic extraction like RCs uh, in the layout. After performing the parasitic extraction, we will move towards the GDS2 file generation.